Hey guys, today we're going to talk about operations and scientific notation. So last week we worked on just putting big numbers and small numbers into scientific notation. This week we need to talk about how we work with scientific notation when we're using different operations such as addition, subtraction, multiplication, and division. Today we're going to just start with adding and subtracting, and there's just a couple of cases we need to look at. The first thing we need to look at is when both numbers we're adding have the same power of 10. That's really optimal. We hope that's the case. And so we'll look at how we do that. So let's say we have something like 4.2 times 10 to the fifth, and we're adding to that 3.5 times 10 to the fifth. As we can see in both of these, our exponent power of 10 is the same. So that's really good. Okay, that helps us out there. And when this is the case, all we have to do is add the numbers in the front and then keep this power of 10 in the problem. So if you think about it, it's 4.2 plus 3.5. All right, we get 7, bring down our decimal, and we get 7.7. So it's 7.7 times 10 to the fifth. Now it should make sense because if they're both 10 to the fifth, then when we add those two numbers, we're adding apples to apples, right? These place values are technically the same because we're saying that we're extending this decimal out 5 places to the right because we've moved it left 5 places. Okay, so we're adding the same things. Like if this number written all the way out is 4, 2, 0, 0, 0, 0, right? So 420,000, and this one would be 350,000. So when we look at that, we're adding the right things up. We got 100,000s, 10,000s, thousands, hundreds, tens, and ones. So that's a fair comparison when we're doing that. Okay, and the rules don't change when we're doing subtraction as long as these things are the same. We can do the same thing. Let's just use the same problem, but let's say that now we're subtracting them. 4.2 times 10 to the fifth minus 3.5 times 10 to the fifth. So that's really nice. All I got to do is subtract the two numbers. All right, borrow here, the 12 there, bring my decimal down. 12 minus 5 is 7. 3 minus 3 is 0. So then our answer here would be 0.7 times 10 to the fifth. Unfortunately, we're not always going to have this be the case. It's really nice when it is the case, but sometimes it's not. But if it's not the case, we can handle it as well. So it's not like we need to really freak out. We just need to change some things to make it work. Okay, so what I'm talking about here is, let's imagine we have this case where the powers are a little bit different. So I'm going to use the same numbers because they're just really nice, easy numbers to look at. So let's say I have 4.2 times 10 to the fifth, but I'm adding that now to 3.5 times 10 to the fourth. So now we can see we have this issue where our powers don't match up. Okay, but we just need to take one simple step to make them match up. Now, if we think about this in the right way, all right, we're going to just rehash the rules. If I move the decimal this place, right, I'm adding positive exponents, right? So I'm making this number bigger when I move the decimal that direction. And the same goes if I want to move the decimal this direction, I'm subtracting from my exponent, right? So if I were going to move the decimal over, then I'm going to be subtracting from the exponent. So if I move this here like that, then this would be 10 to the third, right? And the same thing goes here. If I move this over to here, this is 10 to the fourth power. So I can decide which way I want to move these so that they match up. So if we think about it as 3.5 times 10 to the fourth, this is the fourth, this is the fifth. I think it's easier for me to move this decimal place over to here and then adding 1 to this. So if I'm going to rewrite this now, then I'm going to have 4.2 times 10 to the fifth, and now I'm going to be adding to that 0.35 3.5 times 10 to the 5th. Well, now I have exponents that are the same. So with the exponents the same, now I just add these numbers. I use my rule from the previous discussion we had. So that gives me 4.2 plus 0.35. I'm just going to add in my zeros. And I get 5, bring my decimal down. 4 plus 0 is 4. I get 4.55 times 10 to the 5th. Okay? And again, we could do the same thing if we just wanted to change that to subtraction. All right? We would have the same numbers. So it'd be something like 4.2 times 10 to the 5th. And we would be subtracting 3.5 times 10 to the 4th. But again, remember, I'm going to move this decimal over one. And if I do that, then I can just add one here. That's the rule we're showing here. Okay, so I could rewrite it as 4.2 times 10 to the 5th minus 0.35 times 10 to the 5th. All right, and then I just use that same rule. But instead of adding, like I did here, I'm going to be subtracting. So let me just give myself a little more space real quick. Okay, and now we can see I just do 4.2 minus 0.35. Again, just put in the zeros for the place values that don't have a number just to hold the place. Okay, I can't do that, so I borrow. 10 minus 5 is 5. Can't borrow or can't subtract from 1, so I borrow again. 11 minus 3 is 8. Bring my decimal down. 3 minus 0 is 3. And in subtraction, I get 3.85 times 10 to the 5th. And so that's really nice. And all we're really doing is we're just making it so that when we do the multiplication, or I mean the addition, that we're doing it with an apples to apples addition. We're not adding, 10,000s to 100,000s or 100,000s to thousands. We're actually adding 10,000s to 10,000s, 100,000s to 100,000s. So it's really important if they have different powers that we make sure to move the decimal place to match the power. And it's up to you if you want to go either direction. Obviously, if you're going to go back one, you want to change this one. If you're going to go up one, you want to change the smaller one. So you got to make the choice. Now let's take a look at what would happen if we were multiplying and dividing with scientific notation. This process is a little more simple than adding and subtracting, but we just got to remember our commutative property. Right, and commutative property tells us that we can move multiplication around and decide how to do it based on how we move it, which makes it easier for us. So if we keep this commutative property in mind, and let's just look at another example. Let's say we have 2.1 times 10 to the 4th, and we're going to multiply that whole thing by, we'll put parentheses around it. Let's say we multiply that whole thing by 3.2 times 10 to the 3rd. Now you'll notice here, I don't have to worry so much about the exponents not matching up. Because if you think about it, I know in scientific notation we use the x, but that's still multiplication just like the dot is. So really, if we just eliminated the parentheses, we can move these around. We could switch this one here, and we could put this one here. And then what we end up having is 2.1 times 3.2 times 10 to the 4th times 10 to the 3rd. Now, to evaluate this problem, right, we just use what we know. We know how to multiply these two numbers, so we'll do the scratch work over here. So 2.1, 3.2. I have two decimals, so I'll just keep track of that over here for the end. 2 times 1 is 2. 2 times 2 is 4. Go to the next spot, my place marker. 3 times 1 is 3. 3 times 2 is 6. So I get 2, 7, 6. And I know I'm going in two places. 1, 2. So I know that this is going to be 6.72. All right, and now I got to work out this. Well, I know from my exponent rule, same base, different exponents, and multiplication, that I just add the exponents. So then what I get is this is going to be times 10 to the 4 plus 3. Okay, and that just becomes 6.72 times 10 to the 7th. So that's really nice. So basically, to make this as kind of like a procedure, all you're going to do is multiply the numbers in the front by each other, and then you're going to add the exponents of the powers of 10, and then put that together with the number you get from multiplying the decimals. And that's what you can see that I got here. Let's talk about what we do when we have to divide using scientific notation. It's not much different than multiplication. We're going to treat the two sections of scientific notation pretty much the same. So when we're looking at stuff, we're going to see it written as a fraction. I believe I told you guys this in 6th grade. Moving forward in math, you're going to start seeing the division symbol a lot less, and you're going to see division start to be expressed as a fraction more often. So for a problem like this, you might have something like 3.2 times 10 to the 5th divided by 8 times 10 to the 3rd. Okay, again, just remember that fraction bar is telling us we have division. So we're going to treat it the same way. I'm going to work on these two together, and then I'm going to handle these two parts together. Oh, got a little sloppy there. So the first thing I want to do is I want to do my 3.2 divided by 8. So I know 8 doesn't go into 3, so I put in a 0, bring my decimal up, and I know that 8 goes into 32 4 times, so that gives me 32. I subtract, I get 0. So I know I'm going to have 8, because that's these, so those are done. And now I treat these the same way I've known how to treat them from last week's exponent rules, right? If I have 10 to the 5th divided by 10 to the 3rd, then that's the same thing as 10 to the 5th minus 3, right? And so that gives me 10 squared. And so that's what I just add into the end of this here. It'll be 8 times 10 squared. So just like when we're talking about multiplying, when we divide scientific notation, we really just treat the numbers in front as a division problem, and our solution goes here, and I definitely wrote that in wrong. And then we handle the second part of the scientific notation, and we get 10 to the 2nd. So really it should have been 0.4 times 10 to the 2nd. So this would be the actual solution.